Hello everyone and welcome to this video. Today we're gonna cover the triple integrals and rectangular coordinates. So let's say we have a function w equals f of x, y, z, and let it be defined on a rectangular box. So let's imagine a rectangular box and let it be defined on that box. So the box is basically b, x, y, z, where x is bigger than a and smaller than b, and y is bigger than c and also smaller than d, and z is bigger than r and smaller than s. And so if we draw a coordinate here, coordinate axis, as you can see, x, y, z. Now if we can draw this axis, we're gonna say that A is gonna be here, the x, and B is gonna be here. And now for the C, we're gonna have, so let's do it in a different way. Let's do this, let's draw lines. Let's draw lines. So here we have x equals a, and here we have x equals b. Now this is for the x's. Now for the y, we're gonna have c, which is this line. Okay, y equals c. Then also we're gonna have y equal to d. Now for the z, we're gonna have z equal to r. Okay, and that we can do basically like that. So this is also should be a should be a horizontal line. So let's say gonna have z equal to r and z equal to x. And so these are the boundaries of this rectangle. And now it's bounded in the z and bounded in the x and bounded in the y. So it's a rectangle. Now, if you want to divide this rectangle B into even smaller boxes, so we're going to divide it into AB, this interval, to n subintervals, okay, ranging from xi minus 1 and also xi, so delta x equals xi minus xi minus 1. And we're gonna divide also the y coordinates into m subintervals, so yj minus 1 to yj. And so delta y, so this is our little box. This is our little box, and we do have delta yj, we do have delta x I, and we do have sorry, this is delta yj, and then we do have delta zk. Now this is our little box, which is a part of our bigger box. Now we do have also delta yj equals yj minus 1. And also we can divide the limits of our z boundaries. So we're gonna divide rs into l subintervals. So it's gonna be zk minus 1 to zk. This is one subinterval, this is another, and this is another. These are just one of the subintervals that we're gonna divide this whole rectangle. And so we do have delta zk equals zk minus 1. And so using this definition, we can define what we call the triple integral of f over this box. And so this is basically our triple integral. So as the name suggests, it has three integrals. okay, and the function could be in the x, y, and z plane, and we integrate over dv, which is a very small volume, very small volume part. So it's basically, this is delta v. Delta v is delta zk times delta xk times delta y, sorry, delta y j times delta ki. And so that's our volume k, so say delta v. Okay, and so if we take the limit, so if we take the definition of our integral and take the limit, we're gonna have basically k equals 1, and then L, we have j equals 1, m, and I equals 1 and n. So we're gonna start from these and end up to L and m and n. And so we have this function here, which is basically the definition, and we're gonna substitute in kijk, so x at kijk, so these are specific values for I, j, k, okay, and this is 1 square, the value of x at 1 square, and there is also the value of y at that square, and the value of z at that square, because we are talking in 3D. So we're gonna have x and y and z, and for each one of these we're gonna have specific coordinates in x and y and z. And so this is basically similar to our integral definition in 2D and 1D. So it's very similar. We're gonna use the star here to indicate that this could be the endpoint value of the cube. So it could be here, it could be one of them, but it could be in the center. Okay, so this is basically just one point. And so, and also we multiply this f value by delta v I j k, which is the very small cube that we have here. And so when we multiply each small cube by the value of x, y, z, we get something like an extension of a cube. What do you call it? So we call it, see something, I'm gonna show you now. So it's like a box. So we get a box when we do this, since this is f of x, y, z, and this is just our box. And so when we multiply this small box delta v by f of x, y, z, we get this whole big box. And so also we need to make sure that p, which is basically the square root of delta xi squared plus delta yj squared plus delta zk squared, approaches 0. Okay, and so yeah, so I is between 1 and n, j is between 1 and m, and k is between 1 and l. And delta d I j k, so basically this differential, okay, the small differential, I all squared plus delta yj all squared plus delta zk all squared. And so basically this is using the definition to try to define our triple integral. And at the end, after doing all of this and defining the integral with the limit and all of that, trying to get this value, we're gonna reach to Fibon's theorem, which is basically this. So Fibon's theorem states that the triple integral of a function over a box, okay, which is b dv, is basically the triple integral of that same function over the expanded differential dx, dy, dz, taken at the boundaries of this box that we are integrating about. So our box we said was going in the x direction, so our first differentiable is dx, so our box is gonna go from a to b. This is our first differentiable. And then for the y, we said our box is gonna go from c to d, and from the z, our box is gonna go from r to s. And so yeah, so the iterated integral on the right just mean that yeah, so this integral basically mean that we integrate with respect to x, but we also keep y and z constant, so same comparable to partial derivative, but here we are integrating, and so we have dx, we're gonna integrate keeping y and z constant and integrating with respect to x, and then after that the function we get from this, we're gonna then integrate with respect to y. We keep x and z all constant. So we keep x and z constant, and then we do the same for the z. And so basically we get this value from here, and then this value is gonna give us basically the triple integral. And the triple integral is useful in, for example, finding the volume. It's another way of finding the volume. Now, okay, so here is our box. This is our box. This is our D. And as you can see, this is what I was talking about. xk, yk, zk. Now here, this represents the point at the middle, which was here in our definition. It represents the point at the middle of this. And so we do have also delta yk. This is the change in delta y. Delta xk, the change in delta x, and delta zk, the change in delta z. This can be basically the differentiables if you go to infinity. If you take n as infinity, or you take these, make them go to 0, you're gonna basically get the differential dy. And so this is basically the way we partition a solid with rectangular cells of volume delta vk. And now here we have our definition. As we said, if we want to find the volume, we have a bounded region. So let's say we have this. Okay, so we have this, kind of this. It's a 3D. So this is a 3D object. Okay, not a 2D, since 2D objects have no volumes. They only have areas. And so let's draw, for example, a sphere like this. Or let's draw a box, or an inverted home like this. Whatever that could be, whatever object that could be. And let's assume that we have a function representing this little inverted home that we have. Another object like this is usually modeled like a rock or solid, something like or a baseball, call it, So any object in 3D the volume of it can be obtained using this formula. Now, of course, given that we do know the boundaries of our region, and we do have a function representing that, so these are our conditions. Okay, so we're gonna solve the first example on type 1. We need to find the region that lies between the graphs of two continuous functions x and y. So this is our first example. Now, as we can see here, we have this example. We're gonna solve it. It's an easy example, so we need to evaluate this integral from z to dv, okay? And we have the 4 planes, x equals 0, y equals 0, z equals 0, and x plus y plus z equal to 1. Now, the way I would do this is I'll start to draw first this region. Need to visualize this region. So we'll go like this. And then I'm gonna draw first this plane, so x plus y plus z, so it intersects x at 1, intersects, so this is x, y, and z, and intersects also y at 1, which is here, this point, and intersects z at 1. And so when we connect the points, we get a shape of a tetrahedron. And so this is a tetrahedron. Maybe we can draw it in a better way in order to visualize this. And so it's basically something like this. So these are our axes. Now this is our tetrahedron, and these axes are just showing them as hidden lines, so you can really see how is it looking. And so this is our tetrahedron, and these are this is in 3D. Now if we also need to draw them in 2D, so in the XY plane we do have this. Okay, so 1 1, it's better to draw them in 3D and 2D. And now let's do just basically, yeah, so basically now we're gonna have the integral, okay, the triple integral, and we're gonna add first let's write z, and then we do dz, dy, dx. Now this was required this was required in as you can see, there's no specific requirement, it's just we can do them in the Cartesian coordinates. And so for dz, now dz goes from 0, okay, so as you can see here, z is basically from 0, and it goes up to, it goes as a function of x and y, and so it's 1 minus x minus y. Now this is z, and so it's not really one value, it's just a function of all of the other values. And so this is z. Now let's do it for y, and y starts at 0, okay, and then if we have x plus y plus z, which is basically the function that we are drawing, and then we substitute also z equals 0 into here, we get x plus y equals 1, which gives us y equals 1 minus x. And so it's important to note that we should have two variables in the first integral and one variable in the second integral, and basically numbers or no variables at the third integral. So this is the triple integral. So now if we do this 1 minus x, now this is for the y. Now for the x, this is basically just, it goes from 0 up to, as you can see, 1 here. So from 0 to 1, if you draw it from here. And so, yeah. And this is basically the graph. If you take z equals 0, this is also the graph that you're gonna get, which is x plus y equals 1 or y equals 1 minus x. So this is the graph that you gotta get basically when z is 0. You're gonna get it here. So this is the xy, and this is basically the xy. Okay, and that's what we get. Now for the x we said is 0 1. Now let's evaluate this. Is very easy to evaluate. Now first let's evaluate the inner integral. So the inner integral is z, so it's gonna be basically the integral of, so the integral of z is just z squared over 2. And now we're gonna do z, so we're gonna do z squared over 2 evaluated at z evaluated at 1 minus x minus y minus 0. So it's gonna be basically 1 minus x 1 minus x minus y all squared, okay, divided by 2, minus 0 all squared divided by 2. And then we get the other boundaries, and so dy dx. And so here we can do some simplification. So 0 here just becomes, and if you don't get how we did this, so basically the integral of z dz from 0 to 1 minus x minus y, this becomes z squared over 2 evaluated from 0 to 1 minus x minus y, and this is basically what we are having here, or so 0 squared over 2, this is what we are having here. So basically that's how we evaluated. And now let's continue with our triple integral, try to find the volume of our tetrahedron. And so here this is 0, and here we can take 1 over 2 to the outside. This is one of the properties of the triple integral. We can take any constant to the outside, and so dy dx, and then 1 over 2 here to the outside. And now here, so we're gonna integrate now. So basically we're gonna integrate with respect to y and take x as a constant. So we're gonna have basically the integral of 1 minus x minus y all to the 3. Okay, so this is the chain rule, divided by 3. Okay, and we have 1 over 2 on the outside, so it's gonna be just 1 over 6 on the outside. And then this one, okay, and then minus 1 minus x. Yeah, so basically this, and then we're gonna want it evaluated at 1 minus x to 0 dx. So now we can evaluate this. So we're gonna get 1 over 6. Okay, and we are evaluating y, so y equals 1 minus x, and y equals 0. That's important. We do not want to plug it into x. So we have first 1 minus x minus 1 minus x all to the 3 minus 1 minus x all to the 3. And we took, as we said, 1 over 3 to the outside. And so this one basically is 1 minus x minus 1 minus x is 0. And this remains. And so we get here, also here there are some bodies, so 0 to 1. And now we'll just have this value that we're gonna try to evaluate. And yeah, so we're gonna have this value that we are going to find, and let's just say 1 over 6, the integral from 0 to 1, and we have a minus sign, 1 minus x all to the 3. Now here it's basically the chain rule, 1 over 6 times minus 1 minus x all to the 4 over 4 evaluated from 0 to 1, and this gives us 6 times 4 is just 24, so minus 1 over 24 of 1 minus 1 minus 1 minus 0 all to the 4 all to the 4. This is 0, this is minus, it goes with minus, so we get just basically 1 over 24, and that's our answer. The volume of our tetrahedron is 1 over 24 units, if you want to say, or just 1 over 24. And now this is basically our first example. Let's just go now to our second example and try to solve that. So we want to try to find the volume of the solid enclosed between the paraboloids. So we can add here, as you can see, our example 2. So we have z equal to 5x squared plus 5y squared. We have z equals to 6 minus 7x squared minus y squared. These are our z values. And then, so these are our z values, and in order to find the volume, the formula is basically this: z dv. This is the volume, and let's try to do that. So the integral, triple integral of z dz dy dx, and z. So first we didn't draw this. Let's try to draw this. So this is basically two paraboloids. Okay, so here this paraboloid is at 6. Okay, so at 0 equals 6. It starts here, and we have x negative and y negative, so they're gonna be going down like this. So this is our paraboloid. Of course, this is in 3D. Okay, so it's gonna be in 3D. However, you're gonna imagine it. Okay, this is not a parabola, this is a paraboloid in 3D. Okay, and so here our other paraboloid is just when xy is 0, z is 0, and it opens up. Okay, so our graph is basically gonna be this area. Okay, and now if we try to draw it, we're gonna have something like this, like no, ice cream cone, something like this. Okay, and then it's gonna be, round like this. So it's not the best drawing, but I hope you understand what is that. And so maybe if we draw it in, this is the x, this is the y, and this is the z. Maybe draw it in the xz plane. Can see really what is this supposed to be. So it's supposed to be something like this, that goes like this. Same here. Now this is in the xz plane. Now if you draw it in the xy plane, you can really see something different. Now the xy plane is gonna be also, it's gonna be something like this. So it's gonna be like a circle in the xy plane. Okay, so x, y is up. Now this is what's gonna look like from the upper view. If we're gonna look at this volume from the top, we're gonna see this. We're gonna look at it from the side, from our side, xy plane, so we're gonna see this. Okay, and so now it's dz dy dx. Okay, let's try to do it. Now, okay, yeah, basically we already did it. So now we did this to identify which surface which surface is down, we're gonna put down, and which surface is gonna be up. And basically we see that the surface that's really at the bottom is z equal to 5x squared plus 5y squared, and the surface at the top is z equal to 6 minus 7x squared minus y squared. And now, so we're gonna say here if x squared, 5x squared plus 5y squared, and here we're gonna have 6 minus 7x squared minus y squared. And for our y, now if we want to find the y, we need to find the intersection between the two planes. So the intersection between the two planes is gonna be equating just the z's. So we're gonna have 5x squared plus 5y squared equal to 6 minus 7x squared minus y squared, which is basically what we have here. So the function that we get from here is just basically what we have here. It's either a circle or an ellipse. So let's see what is this. Is it a circle or an ellipse? And so we take 7 to the other side. 7 plus 5 is just 12x squared plus 5 plus 1 plus 6y squared equal to 6. And so 2x squared plus y squared equal to 6, and this is basically an ellipse, and so we're gonna get here an ellipse. So we're gonna get here an ellipse. Okay, so let's take, if we take x0, we're gonna have y squared equals 6, or y equal to square root of 6, or somewhere up here, square root of 6, let's say here. If we take y0, we're gonna have x squared equals 3, and so x equals square root of 3, so it's gonna be a vertical ellipse. It's gonna be a vertical ellipse. Okay, so this is in the xy plane. And now this is what we're gonna see if we gonna see from the top. So it's not a circle, it's an ellipse. Okay, could be a circle, but since here we have different coefficients, so it's an ellipse. And now we just can basically find the y from here. So y squared equals 6 minus 2x squared, and y is just square root of 6 minus plus minus square root of 6 minus 2x squared. So we have a plus and we have a minus. So for the minus, we gotta put it down. So minus square root of 6 minus 2x squared. And for the positive, we're gonna have just positive 6 minus 2x squared. And now, yeah. And so we have just one variable for our second integral. And for the x, now for the x, we need to find first, we need to find the intersections here. We need to find this and this. What are the intersections with the x-axis? And these simply can be done, this simply can be done by letting y equal 0. So y equals 0 will give us square root 6 minus 2x squared, or 0 equals 6 minus 2x squared. So 2x squared equals 6. So x squared equals 3, and x is just plus minus root 3. And so we're gonna have minus root 3 and root 3. And that's basically the volume. Now if we want to evaluate this, we need to do some integration, which I hope is not, it's not hard. Okay, so let's just copy this. So now this is our volume. Let's evaluate this. So v is gonna equal first minus square root of 3, root 3, then minus root 6 minus 2x squared, root 6 minus 2x squared, and then we're gonna have 6 minus, yeah, we're gonna have this, so yeah, so 6 minus 7x squared minus y squared, all squared over 2, minus 5x squared plus 5y squared, all squared over 2, dy dx. Now let's take 1 over 2 outside to make our calculation simpler. So v equals 1 over 2. And now we have this. Now how do we integrate this? So should be relatively easy. So equals 1 over 2. Okay, so we need to integrate something like this. Now how do we do that? Think of a way of doing this. And so okay, so we have like c plus y squared over 2, something like this, and we need to integrate it. Now we can do something about this, and we can just, you know, we can just expand the brackets. Yes, we can expand the brackets, but I want to try this. Let's see if it works. I'm gonna just do something like 6 minus 7x squared. I'm not sure if I don't think this will work. Over 2 times minus 2y. Sorry, 3 to the 3, 3. And now if we try to differentiate this, let's try to differentiate this with respect to y. So partial differentiation with respect to y. It's gonna give us just, yeah, so here 3, yeah, so here 3. So it's gonna give us 6 minus 7x squared minus y squared all to the 3, all to the 2. We're gonna have 3 here, we're gonna have 3 here. And also we're gonna now multiply by minus 2y. And here we already have minus 2y. So basically minus 2y is gonna be like that. We multiply that minus 2y. Basically this is the chain rule. We're gonna cancel this, and we're gonna get back our 6 minus 7x squared minus y squared. So this is basically the way to do it. This is our integral. And this is a very interesting way, an intuitive way to find the integral of such functions. So 5x squared plus 5y squared, you just try to see how would it turn out if you differentiate back. And so 3 times 10y, and you have, so this is dx, okay. And then yeah, so we can, now if we differentiate this also we're gonna get something similar, so we are correct. Now we can take a 3 to the outside. It's 1 over 6. Now let's do this now. Okay, but we want to evaluate this at minus 6 minus 2x squared and square root of 6 minus 2x squared. This is gonna be a bit complicated. Yeah. I think it's doable. Yes. It's doable. So v equals 1 over 6. Now root 3, root 3. Now we will have basically this. Well, it's gonna get a bit complicated, but let's just try to reach out to a place where we can at least try to do this. So minus, so if we start with minus 6 minus 2x squared, so it's gonna be minus 6 plus 2x squared. Okay, so we square this, we're gonna get 6 minus 2x squared. With the minus sign is gonna be minus plus all to the 3 divided by minus 2 square root of 6 minus 2x squared. Okay, and then minus 5x squared plus 5 times 6 minus 2x squared all to the 3 divided by 10y. Now we take this and we do now for our other yeah, so for our other, now here is positive, here also we forget, so it's minus sign, minus 6 minus 2x squared. It's gonna be here basically the same thing, 6 minus 7 x squared minus 6 plus 2x squared all to the 3 divided by 2 times 6 minus 2x squared. Now as you can see, we're gonna do minus 5x squared plus 5 times 6 minus 2x squared all to the 3 divided by 2. Of course, here we have a negative sign, and here we have just a regular 6 minus 2x squared. And now here we have dx. Well, this is interesting. So we're gonna should see some cancellations here, okay? And so this is positive. It's gonna be positive, so positive, positive, and then this is positive. And here we do have negatives. Here we have a positive also. So no cancellations, just a regular integral that we are trying to find the value for. So v equals 1 over 6, integral from -3 to 3 of, let's try to simplify. So first we do have, we can just, and here is 10. So we can have a common denominator of 10 root 6 minus 2x squared. So this is a common denominator. And now we multiply this by 5 in order to get that. So, and then we have minus 7x squared. We have 6 minus 6 is just just 0 here. And then minus 5 x squared all to the 3 plus, now we have 5 by 6 is 30, and we have 30. Now 5 times 2, so minus 10x plus 5x, so minus 5x squared all to the 3. And then we have plus, which is the same as we got here. So first we multiply by 5, and then we do minus 5x squared all to the 3. And we do plus 30 minus 5x squared all to the 3. Now we do have some simplifications here. I'm just worried how are we going to solve such a... No, it should not be worrying. So 6 minus 2x squared. And now 5 to the 3 is just 5 by 25, 125. And we're gonna have a negative sign at the end. So negative sign. And then we're gonna have 5 to the power of 4, which is minus 6 to 5, x to the 6. And we multiply that also by 5. Oh, sorry, multiply that by 2, so times 2. So we have minus 250 squared. So I added these two. And now for the other one, we have plus, just let's say 230 minus 5x squared all to the 3. Now, if we're gonna say we want to integrate this, how could someone approach this? So if we say u equals 6 minus 2x squared, so du is gonna be just minus 4x. And I do not see minus 4x here. So maybe we do something like trigonometric substitution. Yes. So I think we're gonna need something like trigonometric substitution in order to solve this. And it's gonna be, looks like it's messy. Now we can use something like 1 minus, what's the most suitable thing? Now we have sine squared theta plus cosine squared theta equal to 1, and we have also, if we divide this by sine over, if we divide this by cosine, we're gonna get tan theta equals 1 plus 1 equals secant theta. Okay, or we have 1 plus cotan theta equals cosecant theta. And basically, yeah, so we can have here tan theta. We can use this. Secant, so yeah, tan theta will equal to secant theta minus 1. And we need something with 1 minus secant theta, so we can have minus tan maybe. Can have sine squared, cosine. No, we can use the sine and cosine. We'll use the sine and cosine because they, let's say the sine, okay? So we're gonna let x equals sine. Of course, we want this to become 6, so we're gonna have just 1 over root 3, and I'm gonna tell you why it says, sorry, yeah. So root 3 sine of theta, this is the value for x that we can use here, okay, to give us a value that you can use. And so when we substitute, for example, here the square root, now let's do the square root of 6 minus 2x squared. We add 6 minus 6 sine squared of theta, which is basically square root of 6 times 1 minus sine squared, and this is basically cosine squared from our identity here. So 1 minus sine squared is cosine squared, so this is square root of 6 cosine theta. And now we just can substitute in, and for our, here, let's go back to our volume. It's gonna be the integral from, now this has gotten very complicated, okay, but that's how you basically can solve it. So 10 times square root of 6 cosine theta. Now for the rest, so minus 1 250 times, so yeah, so 3 6 over 2 times sine to the 6 theta plus 230 minus 5, so times 3, so 5 times 3 is 15, and we're gonna have, yeah, gonna have here sine squared of theta. Now how do we go about this to the power of 3? Ho ho ho. 5 times 3 is 15. I wish I had 15 here. Could have been way more easier. So of course we need to find also from dx, so dx equals root 3 cosine theta d theta. So we're gonna add root 3 cosine theta d theta. Now someone gonna figure out how to solve this. I'm not gonna do that, but someone, if you are interested in this and you wanna really solve this, then the floor is yours. So basically I think the most suitable way to deal with this is just to do another substitution, maybe do another substitution, to say that maybe sine theta equal to 1 over 2 cosine theta, so something like this. you're gonna try to solve it. You can expand it. You can, expand it and try to find the whole thing. But I'm not gonna do it. So the most important part, well, this is basically for your knowledge. The most important part is this. I'm gonna just plug this into calculator or an online, evaluator. It's gonna give us the value. So this is our value. Now there's another example. Now let's go to type 2. So integrals with type 2. So yeah, so the region lies between the graphs of two continuous functions of y and z. So for our example 4, we're gonna find the volume of the solid that's bounded by the circular parabola x minus y squared plus z squared, and the plane x minus 1. Oh, x equals 1, sorry. So let's copy this as the example. I have some hair on my iPad. Let's go here and do this example. It appears to be a very, very, very simple example. I was surprised that the whole lesson is very simple actually, it's just substitution. And then the integral is basically, you don't need to worry about it since we have a lot of calculators now online that can deal with the integrals, like for example Wolfram Alpha. It's one calculator that deals with integrals and it does all the work for you, so you don't need to worry about that. And so you can find the volume x equals y squared plus z squared. Now we have and x equals 1. Now these two, we can draw them. Now that's interesting. This looks like a paraboloid. Yeah, this is a paraboloid. But it's different in that it is our paraboloids here were in the xy. Now here is gonna be in the yz. And so in the yz, y and z, in the yz, they're gonna not look something like this, it's gonna look something like, so we had it like this, xy, now it's gonna have them, oh, so we're gonna have them like this. No, we're gonna have them in the direction of the x-axis. So we're gonna have them like this. Now this is our paraboloid, this is in 3D, this is not a parabola again. I'm insisting this is paraboloid, so it's gonna be something like this. If you cut it from this side, it's gonna be like this. There's a paraboloid. A paraboloid. Repeat after me. Paraboloid. Now, it's gonna look like this. We're gonna go through x-axis. Since when we had the paraboloid in the... Now we have it like z equals, or x equals y squared plus z squared. Now here we're gonna have it like this. Sorry, we had it like this. We had a z equals x squared plus y squared. And so the axis was x. Now here the axis was z. Now the axis is gonna be x here. And so it's gonna look this yeah, how it's looking there. And so that's very easy. That's very easy. That's a different type of, integral. Now if we draw them also, so it's bounded also by x equals 1. So this is x equals, no, this is x equals 1. It's like a bit of a weird region. Oh. So basically that's what I did. That's the volume. Since this is the plane x equals 1. Let's assume this is the plane x equals 1. X equals 1. And this is our volume. It's gonna look something like this. This shape. And this is the volume. Okay. Now basically it's just, the volume is just the triple integral of z dv, which is v equals, I'm not gonna evaluate it, I'm just gonna write the the limits dz, dy, and dx. So for dz we're just gonna get our little function x equals y squared plus z squared, and we're gonna have now write it in terms of z equals x minus y squared square root of plus minus, okay, and so we can have minus x minus y squared and x minus y squared plus minus, okay. And now, okay, so basically here let's draw our xy y. Now the xy is gonna look something like, we're gonna look at it like a parabola, so something like this. This is in the xy. It's gonna look like this, and this is our x equals 1. So this is our region in 2D. Now, for this to happen, we'll need to have x equals 1. Okay. So, we have x equals to 1. Now we need to find the y. Now the y is just, should be a parabola. Okay, so let's take, for example, maybe I should have changed the limits. So the order of the limits, I could have changed it. So we start with x, and then we go to y and then z. So I could have changed that. Okay, so why is this called a type 2 region? Let's now understand why is this called a type 2 region. Now a type 2 region, this is called a type 2 region because it's in terms of x. Okay, the function is in terms of x. Now a type 1 region that we did a couple of examples here, the example was in terms of y, or in terms of z, sorry. So type 1 functions in terms of z. In type 2, we're gonna have functions in terms of x. And now, in order to integrate, we're gonna start with our function here, the inner integral. We're gonna not start with z, but we are going to start with x. So x dx, dy dz, or dz dy, doesn't matter. But what matters here is that we should start with the function that's written, okay? So the first function that we're gonna use, so here just gonna be basically something like, no, y equals 4, let's say, dz dy, okay. I'm just reviewing the way we do this. So it should not be that complicated. Also, we can convert to polar coordinates. So there's more than one way to do this. Now let's do it our way now. V equals the integral, triple integral of x dx. We already wrote that. Let's just do this. So let's start from x equal to y squared plus z squared up to 1. Okay. And let's just go from there. And now let's find the y. Let's find the y. The y is gonna be basically just, if we let z equal to 0 or x equal to 0, gonna have y squared plus z squared. And now the y is gonna be y squared is gonna equal to minus z squared. So y equals plus minus square root of minus z squared, which doesn't make sense. And now we really bump into an issue. So x equals 1. Maybe if we substitute x equals 1, let's think what we should do. When we substitute x equals 1, we're gonna get something like this. We're gonna get a circle. So this is the YZ plane. So this is our circle, and this is something that's doable. So now this is, yeah, that's how we should do it. Y squared equals 1 minus z squared, and then y equals plus minus 1 minus z squared. And now these are our limits for the z, or yeah, for the y, and so minus 1 minus z squared, and square root of 1 minus z squared. And finally, for our y, if we let y equal to 0, gonna have plus minus square root of 1 minus z squared. It's our circle. So 0 equals 1 minus z squared. And z is just plus minus 1. And so here we have minus 1 up to plus 1. And that's our volume. That is our volume. Indeed. That is our volume. Okay. Now, if we want to evaluate this, let's try to evaluate this. But now I'll do something else. I'll try to make this integral easier on you. We're gonna go y squared plus z squared. And here we're gonna go to 1. So the square root of 1 minus z squared is minus 1 minus z squared, positive, minus 1 plus 1. And we have x dx dA, okay, or just dy dz. Okay, and we can do dz dy, but we did dy dz for some reason. And then, okay, so let's evaluate this integral from the inside. And I'm going to show you now how are we going to not bump into the issue that we bumped into, which is the trigonometric integration and implementing all of these, techniques. Now we're gonna try to find a way to, make it easier for us. So here we're gonna have basically x squared over 2, y squared plus z squared to 1. And so 1 over 2, y squared plus z squared all squared over 2 minus 1 over 2 dy dz. Okay, so actually it's the opposite. So it's 1 over 2 minus, since this is our final, so final minus initial, so y squared c squared all squared over 2. Now if we want to evaluate this, this is gonna be very messy for us, and we don't want something that's very messy for us, so we're gonna do something else in order to fix this. To fix this, we're gonna convert, let's say convert to polar. We're gonna convert the polar, so r squared equals y squared plus z squared. And so we're gonna also convert the ends here. So v equals double integral now, so it's like evaluating an area of 1 over 2 minus r to the 4 over 2 times, now r, okay, r dr d theta. Now this is dA, and we said dA in polar is equal to r dr d theta. And so we do have this. Now r to the 4 over 2, that's simply very easy to evaluate, basically r to the 5, and here just r over 2. And to convert also the ends here, so yeah, 4 minus z squared minus 4 squared, and then 0 to pi. Okay, so here we're gonna have two different things. We're gonna have y equals to r sine theta, or cosine theta, let's say here, and z equal to r sine theta. And now if we just say square root of 1 minus r squared sine theta, or squared, it's gonna be just 1 minus r squared. Yeah. Okay. Actually, what are the ends of our r? R here is just 1. So we're gonna go from 0 to 1. This is from our graph. So this is polar. If we say this is polar and this is our partition, the partition goes from 0 up to r. And so r is 1, so it's from 0 to 1. Now for the angle, it's just from 0 to 2 pi. And that's a very easy, now it becomes a very easy way to evaluate this, 2 pi, and then the integral here now is basically just r to the 5 and r over 2. Now take 1 over 2 outside, we have r, so r squared over 2 minus r to the 5, r to the 6 over 6, and now this is evaluated from 0 to 1 d theta, which is v equals 1 over 2 integral from 0 to 2 pi of 1 over 2 minus minus 0, so 1 over 2 d theta, and this is just basically 1 over 2 or 1 over 4 times theta from 0 to 2 pi, and so this is basically 2 pi over 4 or pi over 2, and this is our volume. This is the volume of our shape, which is this little shape here, and this is the z plane, xyz plane, and the volume of it is just pi over 2, and that's basically how we do it. That's our type 2. Okay, and there is also here our another example. If you want to solve this, you can take a screenshot of this and solve it. Now we have type 3 region, which is the region that lies between the graphs of two continuous functions, x and z. And so we need to evaluate the region bounded by the paraboloid. Okay, paraboloid y equals x squared plus z squared. And the plane y equals 4. Now here this is type 3. Why it's called type 3? Because it's in the direction of y. Now I want to solve this because it's a different question and I'm sure you are curious about how to solve this. So let's solve this. Now let's go to our here. Take this. Crop. Now I'm gonna do this way more faster. Okay, so you're gonna catch up. Try to catch up with me. Integral of d square root of x squared plus z squared dv. And we have y equals x squared plus z squared. Y equals 4. Let's draw this. This is a paraboloid, of course, a paraboloid. Okay, this. Now let's draw it in 3D. Love 3D. Now we live in a world which is three-dimensional, so it's important to know stuff like that. So this is our paraboloid. You're gonna imagine something like this. Try to imagine it, okay? So this is our paraboloid. Looks like a crashed paraboloid. So something like this. Now let's do not in the xy plane, let's do in the xz plane. So this is the xz plane. In the xz plane, we're gonna have a circle. So that's helpful for us in order to convert to polar. We need that. This is our polar, partition. Now let's take this. Let's take the integral and do the square root x squared plus d squared of d. Of course, now we're gonna do dy first, and then we're gonna go do dA. Now dA can be dx or dy. So it is dy dA. It's important to have the first differential to be dy, or the function that we are using here. It's important to have that. Okay, and so dy dA. Let's say we want to have dx dz for some reason. So dy dx dz. Now let's find our y. So y equals x squared plus z squared plus z squared. And also we do have the plane y equals 4, so it's gonna intersect here. And let's assume this is y equals 4. This is our plane. Now it's gonna go from x squared plus z squared up to y equals 4. Now for the x is just gonna be, if we're gonna let y equal to 4, which is our graph here, the circle, which is the upper limit also of our graph. So 4 equals x squared plus z squared. And so the x is gonna be basically plus minus square root of 4 minus z squared. And now this is our limit, 4 minus z squared. And here we have 4 minus z squared, but in the plus. And we do have also finally the z. Now the z, if we let x equal 0, let x equal 0, we're gonna have 0, 4 minus z squared, so z equals plus minus 2. So minus 2 plus 2. Now let's evaluate this. So the integral of minus 2 to 2, integral of square root minus 4 minus z squared, 4 minus c squared, and then so in order to evaluate this integral, I'm gonna just have pi square root of x squared plus y squared. Since this is considered a constant, x squared plus z squared, we don't have any y's. Evaluate it from x squared plus y squared plus z squared up to 4, then dx dz. Now substituting the value to c squared 4 minus z squared, and then it goes now 4 minus x squared minus z squared times square root x squared plus z squared dx dz. How did we do this? So this is basically, if we substitute in these values, we're gonna have 4 times square root of x squared plus z squared minus x squared plus z squared times square root of x squared plus z squared. So taking a common factor 4 and x squared plus z squared, we're gonna have a minus sign. So x squared plus z squared. So this is what we got. Now this is gonna get even more complicated if we continue with this. So we're not gonna continue with this. We're gonna convert to polar. I'm gonna convert to polar. So r squared equals x squared plus z squared. Gonna be minus 2 to 2. Of course, no, the limits are gonna be different. I'm gonna see now what are the limits gonna be. Okay, so but basically here we have r4 minus r squared multiplied by, so r squared square root of r squared, which is just r, times r dr d theta, or just r squared. Now for the r, the limits are gonna be basically, since this is 2 and this is 2, we said our radius is 4, y equals 4. And yeah, so here we have 4, this is r squared, which is equal to r squared, and r squared equals 4, so if r equals plus minus 2, so r equals 2. So it goes from 0 to 2, r. It's basically our partition here. This partition, this is 0 and this is 2. Okay, as for theta, it goes from 0 to 2 pi. Now let's find this real quick. V equals the integral from 0 to 2 pi. Now this is just 0 to 4r squared minus r to the 4. V equals 0 to 2 pi. r to the 3, 4r to the 3 over 3 minus r to the 5 over 5 dr d theta. Goes is from 0 to 2. Now if we take 2 to the 3 is just 8, and 8 times 4 is gonna be using a calculator now, 32 over 3 minus 2 to the 5, which is 32 over 5. Now, how could that be simplified? I don't know. You find your own way to simplify this. I don't care. Now, V equals... No, actually, I care a little, but yeah. So, this is yeah. So 32 over 3 using my little scientific 32 over 5. So this is 64 over 15 theta evaluated from 0 to 2 pi, and V is just basically 64 times 2 is just 128. 128 pi over 15, and that's our volume. That's our volume. And so I think we can finish with this. So yeah, basically this is an illustration of one of our graphs. So basically this could be our upper part of our graph. Z equals 8 minus x squared minus y squared. And we do have also different parts in the graph. So it enters at x squared plus 3 squared. Enters at minus square root. Now this is like, if you want to draw it, you're gonna draw something like this. And this is a tetrahedron. So yeah, so the upper part is just, the upper function is just z equals 1 minus 6. Which is very interesting. I like this one. So this is basically one of the things that we drew. Yeah, this is one of the questions that we solve, which is the type 1 question. Let's show you this. I could not draw it for some reason, so let's show it. Just show you exactly what I was trying to show you. Now this one, this is the type 1 that we were trying to do. Now this is the tetrahedron, this is the type 1. So this is the one that I was, this one. So it has an upper z, it has a lower z, which is this z, x squared plus 3y squared, and it has an upper z. And this is the final graph. It's very interesting. You can find now volumes of shapes, or say solids like these. And here also, this is another solid. This is a tetrahedron. I think that's the one we did also. And so that's all. Thank you all for watching. I hope you benefited from this.